Imagine a world where classical physics predicts something utterly absurd, an infinite explosion of energy every time you heat an object. Sounds impossible, right? Well, at the dawn of the 20th century, that's exactly what science believed. This puzzle, known as the ultraviolet catastrophe, nearly broke physics, until quantum mechanics was born. Today, we're diving deep into one of the strangest and most important turning points in science: blackbody radiation, the ultraviolet catastrophe, and how this problem led to the very birth of quantum physics. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. Let's start with something simple: heat. When you heat up a piece of metal, say iron in a forge, it glows red. Heat it more and it glows orange, then yellow, and eventually white. That glowing light, it's not just a pretty effect. It's a window into the fundamental laws of nature. Physicists in the 1800s wanted to explain this glow with mathematics. They studied a theoretical object called a blackbody, an idealized perfect absorber and emitter of radiation. The blackbody doesn't reflect light. Instead, it soaks up all radiation and re-emits it based only on its temperature. Why was this important? Because blackbody radiation was thought to reveal the purest possible spectrum of thermal light. If you could explain it, you could explain heat, light, and matter all at once. Enter classical physics. Using the tools of the time, scientists like Lord Rayleigh and Sir James Jeans came up with equations to describe blackbody radiation. Their math worked beautifully, at least at long wavelengths, like red and infrared light. But when they pushed the math to shorter wavelengths, like ultraviolet, something went horribly wrong. The equations predicted that as the wavelength shrank, the energy emitted should skyrocket to infinity. Think about that. According to classical physics, any object above absolute zero should be blasting out infinite ultraviolet light. A coffee mug on your desk should fry you with radiation. Clearly, that wasn't happening. This absurd prediction became known as the ultraviolet catastrophe, a complete breakdown of classical physics. At this point, physics was in crisis. Then, in 1900, a German physicist named Max Planck took a radical step. Planck suggested that energy didn't flow smoothly, like water from a faucet, but instead came in tiny packets, what he called quanta. This was revolutionary. Instead of radiation being continuous, it was made up of discrete chunks, each proportional to the frequency of the light. In mathematical terms, Planck proposed that energy equals h times frequency, where h is now called Planck's constant. At first, even Planck himself didn't fully believe in the physical reality of quanta. He treated it more like a clever mathematical trick to fix the equations. But it worked. His formula perfectly matched experimental data for blackbody radiation across all wavelengths. By embracing discreteness, Planck had not only solved the ultraviolet catastrophe, but also cracked open the door to quantum mechanics. Planck's work lit the fuse, but it was Albert Einstein who set off the bomb. In 1905, Einstein applied the quantum idea to light itself, proposing that light wasn't just a wave, but also came in particle-like packets, later called photons. This explained another puzzle, the photoelectric effect, and it gave reality to Planck's quanta. Suddenly, the ultraviolet catastrophe wasn't just avoided. It had become the foundation of a brand new view of the universe. Classical physics, with its smooth and continuous assumptions, was giving way to a world built on probabilities, jumps, and uncertainty. Now you might ask, why should we care about a century-old physics puzzle? Because blackbody radiation isn't just theory, it's everywhere. The glow of stars, the heat from your body, even the cosmic microwave background radiation that fills the universe, all follow Planck's law. Every modern technology that deals with light and heat owes a debt to this breakthrough. Infrared cameras, LED, lasers, solar panels, even the touchscreens on your phone. Without quantum physics born from the ultraviolet catastrophe, our modern world simply wouldn't exist. The ultraviolet catastrophe was more than a math error. It was nature telling us that the old way of thinking had reached its limit. To move forward, humanity had to imagine reality in a completely new way. From the ashes of that catastrophe rose the quantum revolution. Planck's quanta, Einstein's photons, Bohr's atoms, and eventually the entire framework of modern physics. So the next time you see a glowing ember in a fire or look up at the stars, remember, that light carries with it the story of one of the greatest scientific turning points in history. A story where disaster led to discovery and paradox opened the path to truth. And maybe, just maybe, the next catastrophe in physics will lead us to the next great revolution. If you enjoyed this journey into the strange birth of quantum mechanics, don't forget to like this video, share it with a fellow science enthusiast, and subscribe for more deep dives into the mysteries of the universe.